In this module, we'll be looking at the simulation of a flexible manufacturing cell using Simio, the standard Simio simulation package, and then using Simio RPS, which stands for Risk-Based Planning and Scheduling, which extends the standard Simio package by incorporating tool to support real-time planning and scheduling activities. So we'll be looking at both the traditional use of simulation, where we're answering design type questions, and then we'll follow that up by looking at the scheduling aspects, where we are looking at trying to make real-time scheduling decisions. Before we begin our modeling task, we need to first define what exactly we mean by a flexible manufacturing cell. In our context, an FMC is a group of computer-controlled machines interconnected by a material handling system. And the flexible manufacturing cell is designed to produce a wide variety of parts in low to medium volumes. So we have a large number of distinct part types, but each part type is manufactured in a very small quantity. So the FMC consists of a set of stations where the actual part processing occurs, a material handling system, and a group of operators. The stations are comprised of the actual processing machines and part input and output buffers, so parts that arrive to the machine and have to wait are stored in the input buffer, and parts that finish on the machine and have to wait before being transported to the next machine wait in the output buffer. As I said, the material handling system transports parts between all pairs of machines within the system, and a set of operators are required to do some loading and unloading, setup and teardown tasks. So while the machines are largely automated during the processing phase, several require the operator to actually perform a setup operation before the processing starts and a teardown task before the operation actually completes. This is a diagram of our example FMC, and you can see that the system has 4 processing stations and a single operator. In this system, we're not explicitly modeling the material handling hardware, but instead we'll assume that the parts can move between any 2 stations automatically. In addition, we will use an operator pool so that we can easily add additional operators where necessary. So the assumption when we use an operator pool is that any operator can perform any setup or teardown task. You can see in our system that the parts can arrive, so the arrows pointing into a station indicate the arrival of a part. Can arrive to any station, they can depart from any station, and they can be transported between any pair of stations. As I said, the basic idea for an FMC is to support flexible automation so that we can produce a wide variety of different part types, and a part type will be characterized by a particular route through the system. So for example, a part might arrive and be cut, go to the welding station, shaping station, finish, and then depart the system, whereas another part might arrive and be immediately welded, followed by finishing and then departing the system. For our initial model, we'll also assume that each station has an infinite capacity input buffer for arriving parts and an infinite capacity output buffer for departing parts, so that we don't have any blocking within the system. In our initial model, we'll consider 4 different part types, as you see in the following table: part type A, part type B, part type C, and part type D, where a part is characterized by its processing sequence, or what I referred to earlier as the routing, the sequence of operations that the part follows in order to be processed in our system. So part type A arrives at the cutting station, is processed there. Once it finishes processing, it's transferred to the welding station. Once it's completed processing at the welding station, it's transferred to the shaping station. Once it finishes shaping, it moves on to the finish station. Once it finishes at the finish station, it's completed and leaves the system. Similarly, part type B goes through a cut operation, followed by the weld operation, followed by the finish operation. Part type C is cut and then finished, and part type D is cut, shaped, and finished. So the system is designed to produce parts in any sequence. We just chose 4 different parts for this small example. Also note that all 4 parts start at the cut station and finish at the finishing station, and so this is certainly not a requirement set out by the hardware. It's just for our example. And finally, as we mentioned before, each operation in our table has a setup step and a teardown step that require the operator. So for example, when part type A arrives at the welding station, the operator performs a setup, then the operator leaves, and the part is processed by the automated component. Once the automated component finishes, the operator is required to come back and perform a teardown. So that same setup and teardown happens at each one of the operations. Also note that if the automated portion of an operation finishes, such as operation 2 on part A, and the operator is not available, the operator is busy doing another task, then the part will stay on the welding station until that operator becomes available to come perform the teardown operation. In order to construct the simulation model, we need some additional details in addition to just the part sequence, and some of these details are given in the table as you see here. So for each part type, we have 3 basic pieces of information. We have processing time information, we have arrival rate information, and we have product mix information. So for example, the cut operation, the average setup time is 0.4 hours, the average processing time is 3.2 hours, and the average teardown time is 0.4 hours. And we have that same information for each one of the processing steps. And so as I said, these represent the average time for each one of the operations. For the arrival rate information, this tells us that 0.4 parts per day arrive. So roughly every 2.5 days, a part of type A will arrive to our system. The reason we use processing rates rather than processing times or arrival times is the processing rates are additive. So we can add the 0.4 that arrive of part A and the 0.6 for B, 0.5 for part type C, and 0.4 for part type D, and that tells us that 1.9 parts per day on average arrive, and we can use this total arrival information to compute the product mix. So roughly 21% of arriving parts are of type A, 32% are of type B, 26% are of type C, and 21% are of type D. Now that we have the system defined and our example parts set up, let's look at how we'll apply simulation for the system. The first set that we're going to look at are what I would consider to be the traditional applications of simulation, which involve design-type tasks. So these are done often before the system is actually built, trying to assist with the design or perhaps a redesign of the system due to production mix changes, equipment purchases, and so on. Types of questions we answer with this type of analysis include capacity planning, do we have enough capacity to meet our expected demand, and so on. Equipment selection, if I'm trying to compare between alternative pieces of equipment that might have different processing characteristics, and finally layout, trying to decide exactly where in the shop floor I'm going to place the specific pieces of equipment. The second general set of analysis tasks we'll consider are scheduling tasks, and these are newer applications of discrete event simulation. And the scheduling tasks involve setting processing priorities and dispatching rules in order to meet your scheduling objectives, which might be due date based, you might have target utilizations, and so on, and you'd like to set the dispatching rules to use in your simulation model so that you optimize the scheduling objectives. Staffing levels, we'll see that we're going to have significant operator interference problems, so selecting the number of operators to use depending on the processing requirements, developing operation sequences so that you can operate the facility, something we'll also experiment with a little bit. So basically, in general, when we look at the design tasks, these are tasks that are performed on a long time scale. So these are typically done, as I said, before the system is actually in place or during a major redesign. Whereas the scheduling tasks are much more operational in nature, in that we typically perform these tasks on a much more frequent basis in order to meet the day-to-day demands of the manufacturing system.